All right, hello, this is Dr. Bauer again. We're looking at section 2.3 on functions. So maybe with your training in pre-calculus, this will be somewhat familiar territory, although I don't know how far in depth that you covered it in pre-calculus. But so first of all, let's talk about what a function, what a relation is, because we're going to use that definition to then define what a function is. So a relation, according to the definition here, from set A to set B is simply any set of ordered pairs, x and y, where x comes from set A, or x is an element of set A, and y is a element of set B. Another way to say this, a relation is a subset of the Cartesian product, A cross B. Remember, a Cartesian product was forming those pairs where the first thing comes from the first set and the second item in the pair comes from the second set. And that's really what we have with Cartesian ordered pairs, I should say. And so a relation is just a cross product or a subset of a cross product. It doesn't have to have all the different pairings. So a relation is simply any set of ordered pairs. It could be just some of those pairs in the Cartesian product. So an example, a database of phone numbers with names and phone numbers is a set of pairs, an ordered pairs. You have the name coming first, and then the phone number, function. Let's look at an example first. For products in a store, for each barcode number of the product, there's a single weight of the product, right? It's used in those self checkout lines. So when you scan the barcode, you put it on the scale where the bags are, and if the weight is not correct, it signals that to the attendant. So it's true that for each barcode, there's exactly one weight. And that's what a function is, that for each first element, there's exactly one second element. So we call this a function, all right? Now, the definition, the strict definition of a function, a function f from set A, the domain, to set B, the codomain, is an assignment to each element of A exactly one element of B. So that's what makes it a function. If for each first item, there's exactly one possible second item, all right? We write f of A equals B if B is the unique element of B assigned by F to the element A of set A, all right? So set A is this domain, this set of domain elements. Set B is what we call the codomain, or it's called the range sometimes, but this book calls it the codomain. And the function f assigns to each element in the domain an element in the codomain, all right, using that function f of A equals B. So little a is one of the elements in set A, and little b is one of the elements in set B. Now, if f is a function, or also called a mapping or a transformation, mapping means we're assigning one to one, just like a map assigns a location to a spot, or a location in real life to a spot on the map. Anyway, we write f is a function from A to B right here. This this item right here, f maps A to B, or f is a function from A to B. Note that set A, the set of pre-images, is called the domain of F, while only those elements of the codomain B that are images of domain values are called the range. So the codomain might include more than, I'm sorry, the codomain, yeah, is larger, but only those images that have pre-images are called the range. All right. So essentially, a function is a relation in which each x is assigned to exactly one y. Now, sometimes assignments are specified one by one, such as in a table. If you had a table of x values and y values, and for each x there's exactly one y assigned, then that could be a one by one assignment of values. Or a listing of the pairs would be the same thing. If you listed the pairs out horizontally, listing the pairs, that would be a one by one assignment of the mappings. Sometimes a formula is used, such as f of x equals 2x minus 3. Now, there you're plugging in an x, and you're getting an answer for that 2x minus 3 function. You could think of it as the y, but it's basically the image of the x that you plugged in, all right? So you have a set of x's, that's your domain, and a set of y values that are possible, but only those that are plugged into it become the range. And then also a third way to assign y values for each x value is with a computer program. This is an algorithm that can go through some process, take the x and do some process to it, and assign a y. All right. So I'm going to look at some examples in the Rosen text. Okay, so you see on page 140, example 1. Here's an example of a function. It says, what are the domain, codomain, and range of the function that assigns grades to students described in the first paragraph of the introduction to the section? So let G be the function that assigns a grade to a student in our discrete math class. Note that G of atoms is A, so atoms got an A. The domain of G is the set of students. In this case, the names of the students were Adams, Chow, Good Friend, Rodriguez, Stevens. And the codomain is the set of possible grades, A, B, C, D, F. But the range of G is the set of grades that were actually assigned. So no one got a D, and so the range is A, B, C, and F. The grade of D is because each grade except D is assigned to some student. So you understand that the codomain is the possible ones that could be, while your range is the ones that actually were images of the domain values. Example 2, let R be the relation with ordered pairs Abdul 22, Brenda 24, Carla 21, Desiree 22, Eddie 24, and Felicia 22. So this is pairing a graduate student and the student's age. Specify a function determined by this relation. Now these are just single pairings. There's no function or formula that expresses these. So the function has to be just described as I'm highlighting right here. F of Abdul is 22. F of Brenda is 24. F of Carla is 21, etc. So you're expressing it as F of the first thing equals the second thing. All right. Now, the domain is the set of names, Abdul, Brenda, Carla, Desiree, Eddie, Felicia, and the codomain is the possible ages of the students. Now, it's really highly unlikely that the students are going to be over 100 years old. So you could say the positive integers less than 100 would be your codomain, because you can't have ages, anywhere less than 100. But you could choose something else. You could say between 10 and 90 or whatever. Anyway, the range is the ages that are actually used. In this case, ages 21, 22, and 24. All right. Okay, example 3 says, let f be the function that assigns the last 2 bits of a bit string of length 2 or greater to that string. So it basically picks out the last 2 bits, ones or zeros, of the bit string. So for example, here's an example. F of 11010 would equal 10, because it just chose the last 2 bits of that bit string. So the domain of F is the set of all bit strings of length 2 or greater. So that's like an infinite number of possible bit strings of length 2 or greater. And the codomain is all the possible values. Well, you could have 0, 0, you could have 0, 1, you could have 1, 0, or 1, 1 as possible values. So, of course, we don't have a list of what are the specific bit strings that we're plugging in, so you could imagine any could be plugged in. So the range would be, the codomain and the range would both be 0, 0, 0, 1, 1, 0, and 1, 1. All right. Example 4, let f be a function mapping an integer to an integer. So that's the z set is the integers. It assigns the square of an integer to this integer. Okay. F of x equals x squared, where the domain is the set of all integers. The codomain of z, or f, excuse me, is the set of all integers, and the range is the set of all integers that are perfect squares. So the way this is assigned, the domain is the integers, the codomain is the integers, but when you square an integer, you're only going to get certain values of integers. 0, 1, 4, 9, 16, 25, all the perfect squares, okay? Okay, so back to the PowerPoint. Example 5 discusses the integer function, or int function. So you can look at that in more detail in the text, but it's found in almost all computer languages. The domain of this integer function, or int function, is all real numbers. So you can plug any real number into the function, but the codomain is the set of integers. So you can only get an integer out of this. So, like for example, if you plug in 1.7, it'll give you 1. If you plug in 2.3, it'll give you 2. So it always just gives you the integer that is lower than that whatever number you plugged in. So if you plugged in negative 1.7, what's the integer lower than negative 1.7? Negative 2, right? So it'll give you always integer values. Now, a function such as ABS, or absolute value, that finds the absolute value, is considered real valued. That means we can get out of it any real number, or I should say, we can get out of it real numbers. You can't get negatives from the absolute value, but you can get real numbers. In other words, fractions and decimals and square roots, not just integers. Okay, so if you just get an integer, we call it integer valued. But if you can get fractions and decimals and square roots and integers and any number, then we call it real valued. Now, if two functions are of the same type in this regard, like they're both integer valued or they're both real valued, you can add them together. You can add the two functions together if you want. But if they're not, if one's integer valued and one real valued, then you don't add them together. So here are some definitions related to functions. There's several of them. So let in number 1, let f1 and f2 be functions from a to r. Then f1 plus f2, that's the sum of the two functions, and f1 times f2, that's the product of the functions, are defined, are also functions from a to r, defined for all x, an element of a, by f of 1 plus f2 of x equals f of 1x plus f of 2x. Yeah, shoot. All right, let's look at some definitions involved with functions. So, number 1, let f1 and f2 be functions from set A to set R. Okay, so R is like the real numbers, but from set A to set R. Then f1 plus f2, in other words, we're adding the two functions together, and f1 times f2, so we're multiplying the functions together, are also functions from A to R, defined for all x that are elements of A by f of 1 plus f2, so that combined added function equals f of 1x plus f of 2x, so the y values added together. And f of 1 times f of 2, that function's y value, equals the y value of f of 1 times the y value of f of 2. So that's how we defined the product of two functions. It's the product of the y values. Now, item 2 here says let f be a function from a to b and let s be a subset of a. So we have a smaller subset of the domain. The image of that smaller subset S under the function f is the subset of B that consists of the images of the elements of S. So that would make sense. I mean, we have a smaller subset of set A, and then we're applying the function to those items in that subset, and we're getting another subset of the range of set B, a subset of set B. We denote the image of S by the set f of s. So f of s is this subset in the range, within the range subset, within set B, or within the codomain. We call that f of s. Okay, so in other words, we're not thinking of plugging a single one in at that time. We're talking about if we plugged in all the elements of set S in, that would give us this subset of the codomain. So here's it in function or set notation. F of S equals the set of all t such that there exists an S, an element of S, where t equals f of s. So for every s that exists in set S, every element that's in set S, the t is your image value, which is formed by doing the f of s. There must exist an image of the domain element S for it to be in f of s. So for every element in f of s, there is some element that it came from in the domain. Okay, item 3. A function is a one-to-one or injective function if and only if f of a equals f of b implies that a equals b for all a and b in the domain of f. So every time the y values are the same, the x values will also be the same. Okay? Such a function also is called an injunction. Okay, it's called injective or one-to-one. Now, in common language, one-to-one is easier to understand, but this book uses injective, or calling it an injunction. We can express this using quantifiers as, for all A and for all B, if f of A equals f of B, then A will equal B. Or you could say, for all A and for all B, if A is not equal to B, then f of A is not equal to f of B. Now that right there, I don't know if you recognize it, but that's the contrapositive of the previous statement we just talked about. So there's two ways of looking at it. Either that if the y values are the same, then the x values are the same, or if the x values are different, then the y values will be different. Okay? Now, if that's hard to understand with all that symbolism, I've rephrased it in English, what I call non-math English, but there's math in it. But a one-to-one function has two properties. Okay, if it's one-to-one, there's two properties. For each x, there is one y value. Now that's because it's a function. If it's a function, then for each x, there's just one y value. But also, for each y value, there is just one x value. And that comes from the one-to-one idea. Okay? If it's not true, if two different x values give you the same y value, then that's not one-to-one. Because then for that y value, there's two x's. And so it's not one-to-one. All right? So here's an example. Determine whether the function f from a, b, c, d, so that's your domain, to 1, 2, 3, 4, 5, so that's your codomain, with f of a giving you 4, f of b giving you 5, f of c giving you 1, and f of d giving you 3, is one-to-one. Is that one-to-one? Answer, it is, since f takes on different y values for each domain element. So you don't ever have two x's giving you the same y value. The y value of 4 is only comes from A. The y value of 5 only comes from B. The y value of 1 only comes from C, and the y value of 3 only comes from D. All right. Here's another example. Is f of x equals x squared from z to z, from the integers to the integers, is that a one-to-one function? Answer, no. Since when we plug in 1 and square it, we get 1. But also when we plug in -1, we square it, we get 1. So the same y value, 1, can come from two different x values, either 1 or -1. So we say that that's not one-to-one. All right. Item 4, a function is onto or surjective. The book uses this word surjective, or when we want to say onto, if and only if for every B, an element of set B, the codomain, there is an element A, an element of A with f of A equaling B. What this means basically, let's look at the quantifier statement. The quantifier statement says that for all y, there exists an x such that f of x equals y. So that's, in real short symbolism, what we're trying to say. For every y, there is existing an x so that f of x equals y. All right? Now, y is the elements of the codomain. So in other words, all those elements in the codomain are used or have associated with them an x value in the domain. So in English, a function is onto, and therefore surjective, if all elements of the codomain are used as images of domain elements. Okay? So it uses up all the codomain, which is really the same as saying the range is the same as the codomain. Now, is the function f of x equals x squared from z to z surjective or onto? Well, no, because you don't use up all the integers. You can't get any negative values when you square a function. So the whole negative set of numbers, of integers, are not used, they're not in the range. So it's not onto. In other words, filling up all the codomain with images. So on page 144, let me go there and look at some mapping diagrams to help you see this. Okay, so looking at page 144 at some mapping diagrams, you see in figure 5, letter A diagram, that A maps to 3, B maps to 4, C maps to 1. So it's 1-to-1 in the sense that for each domain element, there's a range. There's just one range element or codomain element, and vice versa. But it's not onto. It's not surjective, because notice the number 2 is not used up. So your codomain is not all used up. The range is 1, 2, 1, 3, 4, and the range is not the same as the codomain. In diagram B, it's onto because all items in the codomain 1, 2, 3 are used up, but it's not 1-to-1. Why is it not 1-to-1? Well, right here, the item 2 comes from the pre-image item A and from D. So both A and D give you 2, and so that's not 1-to-1. The next example shows something that's 1-to-1 and onto. There's just one line connecting, a domain item with a codomain item, and every one of the items in the codomain are used up. 1, 2, 3, and 4 are all used up. So that is both 1-to-1 and onto. The next picture shows one that's neither 1-to-1 nor onto, because the number 2 comes from either A or C, so that's not 1-to-1 function, and also the number D is not used, so it's not onto. You have to have all the items in the codomain used up for it to be onto. And then last of all, this pictures something that's not even a function in the first place, because the X being A, the first element being, or item in the domain being A, gives you 2 possible Y values. A could equal or give you 2, or A could equal 4. So this is not even a function at all. Okay, so back to the PowerPoint. Item number 5, a function is a one-to-one correspondence, also called bijective, involving both 1-to-1 and onto. So it's got both of those properties. It's called a one-to-one correspondence or a bijective function. Then here's an example. Let f be the function from a, b, c, d to 1, 2, 3, 4, with f of a equaling 4, so a goes to 4, f of b goes to 2, f of c goes to 1, and f of d goes to 3. Is f a bijection? Okay, a one-to-one correspondence. Well, as I have in the solution, since as we see in the mapping diagram, each domain element is assigned to one image, and we also see that each codomain element, so the codomain is your 1, 2, 3, 4 in this case, is assigned from exactly one pre-image item. So it's 1 to 1. And since all the domain elements are used up, assigned from a pre-image in other words, then we know F is also onto. So if it's both 1 to 1 and onto, then we call it a 1-to-1 correspondence or a bijection. All right. Now consider f of x equals x squared, g of x equals x, and h of x equals 5x minus 2 from the real numbers to the real numbers. Okay? So I asked the question, which of the three functions are bijective? Which means, of course, 1 to 1 and onto. So let's look at that. So in the first case of f of x equaling x squared, we already talked about this. This is not onto because you can't get the negative values, so it's not going to use up all the real numbers. Remember, this has to be a function. This is a function defined from R to R, the real numbers to the real numbers. So because when you square something, you can't get a negative, then all the negative numbers are not in the range, so it's not onto, and so it's not bijective. In item 2, g of x equals x, that's called the identity function, by the way, because when you plug in x, you get that same value, x. So you plug in 5, you get 5. So it is 1 to 1 since it assigns each x to itself, and so therefore there's no y value that is used twice by two different x values. And it's onto, since all the real numbers are acquired by using that real number for its x. So in other words, for each real number, you just use that same real number for the pre-image or the x value, and so it's onto. So this is bijective. All right, in the third case, h of x equals 5x minus 2 is 1 to 1, injective, since we know that f of a equals f of b. So in other words, if the two y values are equal to each other, which if we plugged in a into the function, we'd get 5a minus 2, and we plug y or b into the function and get the y value for that, we'd have 5b minus 2. So these 5a minus 2 and 5b minus 2 are like the y values that you would get by plugging in a for x or b for x. And then if we solve this equation basically, or basically get rid of the things in this equation by adding 2 to both sides, for example, which will give you 5a equal 5b, and then we divide by 5, you'll get a equals b. So since when the y values are the same, the x values have to be the same, then by their definition of 1 to 1, this is a 1 to 1 function. Okay? And then h of x can also be shown to be onto or surjective, since if k is some image in R, let's suppose we give a name to some image in R, call it k, then there exists a preimage for k. Why? Well, okay, let's imagine x is the preimage, the x value, and so 5x minus 2 must equal the y value, k. Okay? So solve this. Well, if you add 2 to both sides and then divide by 5, you get x equaling k plus 2 over 5, which is going to be a real number in the domain. So for each real number k in the codomain, you will have a x value, it's basically k, that value plus 2 divided by 5 in the domain. That will be the preimage, or the value in the domain that would give you that k value. All right. So we've shown that if you pick a particular codomain element, some real number in the codomain, in the range, we can find a preimage value or an x value that would give us that using the function. So therefore it's onto, and therefore because it's one-to-one and onto, it's bijective. There's another example in the text that you can look at for this. You probably should make sure you can do this, where you can give me an argument why it's one-to-one and onto for this kind of a function. All right. Then another property of functions, sometimes that is true, is that them being an increasing function or decreasing function, or strictly increasing or strictly decreasing. So an increasing function f from r to r is increasing if f of a, the y value for the a value, is less than or equal to f of b. So what that means is those y values as you go to the right will always get higher the more you go to the right, or equal to or higher than the ones on the left. So the ones on the left will always be less than or equal to the ones on the right. Now, strictly increasing means that it will not just be less than or equal to, but always less than. So in other words, that function always has to be increasing and never can even be level. Strictly increasing means you can't have a level spot. You have to always be increasing. Decreasing can mean you're never going up. It's always either going level or going down. Okay, so f of a is greater than or equal to f of b whenever a is less than b. Or if you want to talk about strictly decreasing, it's f of a is greater than f of b whenever a is less than b. So that would mean that you're never going up and you're never going sideways horizontally either. You're always decreasing. That's what we call strictly decreasing. So an increasing function can level off for a while, but not a strictly increasing one. And the same goes for this decreasing and strictly decreasing. All right, item 7. If f is a one-to-one correspondence from a to b, then the inverse function of f, denoted by f, and then you have the -1, what looks like an exponent, but it's not meant to be an exponent really, but it just is the notation for the inverse function. So the inverse function of f, denoted as f -1, or we just say the inverse of f, assigns to each element b in B the unique element a in set A, such that f of a equals b. So in other words, it's going not from A to B, but from B to A. Thus, f -1 of b will equal a. So it's a function that basically goes the opposite direction that the f function does. The f function will go, from an a value to a b value, set A, the domain, to a codomain. The inverse function switches the domain and the codomain around and will go the other direction. Okay, now this is not the reciprocal. The inverse function is not the reciprocal, so don't get confused because of the f negative 1 and think you're going to flip it over. It's a reciprocal. It's just a note. It's an unfortunate notation, actually, I think. But anyway, if a function is a one-to-one correspondence, so in other words, if it's both one-to-one and onto, in other words, if it's bijective, then it's going to be invertible. Invertible means it will have an inverse function. Okay? So if it's one-to-one and onto, in other words, bijective, it will have an inverse. So let's look at example 7. F is a function from set A, which is the asterisk, the percent sign, and the number symbol, or hashtag. So those three are the domain of the original function. And then set B is 7, 8, and 9. So f of asterisk is 8, f of percent is 9, and f of number symbol is 7. Is f invertible? In other words, can we find its inverse function? Well, you need to verify that it's one-to-one and onto. But you can do that quickly by a mapping diagram, and you can see that it's one-to-one, and all the elements of the codomain, 7, 8, and 9, are used, so it's onto. All right, all the elements 7, 8, and 9 have pre-images, and so therefore they're used by the function. So f is onto. So it's one-to-one and onto, so it's a one-to-one correspondence, and so therefore it's invertible. So to find the inverse, we just switch it around. So since the number symbol gave us the 7, so the inverse of the 7 is the number symbol. And because the asterisk gave us the 8, then the inverse of the number 8 would be the asterisk. And because the percent symbol gave us the 9, then the inverse of the 9 is the percent symbol. So you're just switching the order of these things. Okay, now item number 8. Let G be a function from set A to set B. Let F be a function from set B to set C. The composition of the functions F and G, denoted for all A, an element of A, by F, and then you have a little circle G. So F composite G, but it looks like a little circle. You could call it the fog notation, F-O-G, but it's really a tiny little circle. It's not the letter O. It is defined by F composite of G of A is F of G of A. Now, we do things from the inside out when we have parentheses. So you can see that we would do the G of A first, and then the F function when we have F composite G of A. So it really means we're going to do the G function first and then the F function, and that's how we do the composition function. Okay, so in the note, to find F composite G of A, we do F of G of A. We first find the image of the inner function G of A, and then take this result and plug it into the outer function outer function F, to get the final image F of G of A. So in the picture here, I'm a visual person. I like to picture things. But Rosen had this picture in the text. So we have the function G that's done first. Okay. This function G takes element A and does something to it and gives you the image. G of A is the image of A when you apply function G to it. Then take that and plug it into the F function, and we do F of G of A, and that results in our final image in set C. All right. Now the composition function basically does it all at once. It is a way to combine the two functions and do one function going from A to the image of A after you apply it into both of those functions. So that's a picture of what we're talking about with a composition of functions f and g. All right. So we'll look at an example. Oops. So here's an example. Let f and g are functions from z to z, so from the integers to the integers, with f of x equaling 5x minus 7, g of x equaling 4x plus 1. Now it tells you to find f composite g and to find g composite f. Now note that f composite g and g composite f are not the same thing necessarily. Okay, so the order does matter when you're plugging or when you're forming a composition of two functions. So the composition f composite g of x would be f of g of x. Okay, so what we're going to do first is put g of x into the function f. So I wrote down what g of x was, 4x plus 1, that's right here. And then I plugged it in to the function f. Now, do you see that where I have these parentheses, 4x plus 1, used to be where the x was in the f function. The f function said 5 times x minus 7. So in place of the x, I took out the x, I put in a parentheses and stuck in the g function. So 5 times 4x plus 1, that's the g function, and then minus 7. So you're taking one function and putting it into the other function where the x was in that outer function. So then if you distribute, you get 20x plus 5 minus 7. The 5 and the minus 7 becomes negative 2. So 20x minus 2 is the final composition function. All right. We composed it from the other two functions. Now, g composite f of x is g of f of x. So we're going to take the f of x function and stick it inside the g function. So the f of x function is this 5x minus 7 function. I put that inside the parentheses, so now I got to do g of that. Well, g of that means put that in place of x. So you see the g function is 4 times x plus 1. So I go 4 times parentheses plus 1, and in the parentheses, I put the f function, 5x minus 7. So I put that 5x minus 7 where the x used to be. So I've got 4 times 5x minus 7 plus 1, and I distribute the 4, and I get 20x minus 28 plus 1. Well, minus 28 plus 1 equals minus 27. So the composition G composite F is a little different. 20x minus 27 instead of the other function. Okay? So this there's another fact here that's important. When we form a composition of any function f and its inverse f negative 1 of, the inverse of f, the following is true. The inverse, the composition of the inverse and the function is the same as the is the inverse of the function, which if you look at this, what's the function? What's f of a? It's b. And then what's the inverse of b? Well, it's back to a. In other words, we plugged a into this composition of the inverse and the function, and we got a. And also, if you do the composition f composite f negative 1, or in other words, the inverse of b, and you do that, you'll get back to b. So in other words, when you do a function and its inverse together as a composition, it doesn't change the number you plug in. You plug in a number, you're going to get the same number. You plug in A, you're going to get A. You plug in B, you're going to get B. So when we compose or make the composition of a function and its inverse, this only happens if you're composing it with its inverse, then we get what's called the identity function. Or in other words, we plug in a number, we get that same number. So another way to put this is the inverse of the composition of the inverse and the function of x is x. And the same goes if you switch it around for all x. All right, so another definition, what is a graph? Well, we talked about graphs since you're in 7th grade or something like that. But let's get a more precise definition based on the notation we have in the class. Let f be a function from set A to set B. The graph of the function f is the set of ordered pairs A and B, where A is an element of A and f of A equals B. In other words, we're going to set all the pairs where you plug in an A and you get a particular B. And so A, B, those pairs make up the graph of the function. Okay? Now a graph is a relation. All right? Any graph is a relation, and it's a subset of the Cartesian product, A cross B. All right? Now here is a picture of a graph from Rosen's text on page 148. This is the graph of 2n plus 1 from z to z. Okay, so actually this only uses the non-zero integers because there should be a dot right there if it was from z to z. This one goes, if you plug in starting from n being 0, you plug in 0, well, 2 times 0 plus 1 would give you 1, so 0, 1 is the first point on the graph. And then if you plug in 1, you get 3. If you plug in 2, you get 5. So this is a set of certain pairs that are found by plugging them into this function. This is a graph of the x squared function. F of x equals x squared from the integers to the integers. And you see that it's these pairs where the first number is the x and the second number is x squared, or the y value. Now, why didn't it make a smooth curve? Well, because this is from the integers to the integers and not from the real numbers to the real numbers. Now, if we had defined this function from the real numbers to the real numbers, then it would be a smooth curve all the way through on that graph. Okay. Two more functions, the floor and ceiling functions. So the floor function assigns to a real number x the largest integer that is less than or equal to x, denoted by x with these symbols here. And you notice that the line at the bottom of this symbol here kind of indicates the floor. It's at the bottom, all right? The ceiling function will have the symbol with that little knob there at the top, so you think of the ceiling. All right, so what happens is it goes to the greatest, it's the greatest integer that's less than or equal to that number. So let's say if you had 1.9, right? What is the greatest integer that is less than or equal to 1.9? Well, it has to be less than 1.9. So the greatest number that is, or I should say integer, that is less than or equal to 1.9 is 1. So that is why if I go over here to 1.9 for my x value, I go up and it's only at a height of 1 there. Now when I get to 2.0, well, the greatest integer that's less than or equal to 2.0 is 2.0. So 2.0, 2.0, or 2.2 is on the graph. All right. Now, if I chose something like negative 1.3, so negative 1.3 for the x coordinate is about right there. The y value, well, what y value, what's the highest integer less than negative 1.3? It's actually negative 2. Okay, so in the case of negatives, you're always going down to the integer, but you're going to go to the lower negative number. The ceiling function always goes higher. It's a ceiling function assigns to a real number x the smallest integer that's greater than or equal to x. So it's the smallest one that's greater than that value. So let's say 0.4. Right? What integer is the smallest integer that's greater than 0.4? Well, that's 1. So when I have 0.4 here, 1 is the y value. So these are called step functions when it looks like a staircase like that, but there's the floor, ceiling, and the floor function and the ceiling function. Now you can also look at the examples of this in the text. So here's some more examples of using the floor and the ceiling function. So let's just real quick talk about this. What would be the floor function for 1.7? Well, here you go to the integer below that. So the floor function of 1.7 would be 1. The floor function for 4 is 4. You know, it's a whole number, so it's just going to be that whole number. The floor function for negative 2.39, well, we got to go down. You're always going down because the floor function to the next integer below that, which would be negative 3. Letter D, if we're going down to the next integer, well, it's going to be negative 2, not negative 1. If it was positive 1.001, you'd go down to 1, or negative 1. I'm sorry, you go down to positive 1. But since this is below negative 1, we've got to go down further to negative 2 to be at the integer below that. And then here it's 58. Now, for the ceiling function, well, we're going to go up to the integer, the next integer. So it's 2 for A. For B, it's still 4. C, up to the next integer, so that would be negative 2. And up to this next integer, it would be negative 1. And then up to the next integer here would be 59. Okay? Now, an application of this, how many cell phone minutes should be charged when a person talks for 470 seconds? Okay? Well, cell phone minutes are found by rounding up to the number of minutes. So if you talk for 470 seconds, you could do 470 divided by 60, but then you got to round it up. So you're going to use the ceiling function. The ceiling function for 7.83333, which is what you get when you divide 470 by 60, you round that up, so it's 8 cell phone minutes. Okay, so this expression is commonly, something that you would use in computer programs, like, for example, Verizon or, T-Mobile or something could use this computer command to take the number of seconds and divide by 60 and then round it up, and that would be how many minutes are charged. There's other excellent computer applications on pages 26 to 28. I'm sorry, examples 26 to 28 on page 149, and some other important properties on table 1 that you should look at. So I decided to go ahead and look at example 27 in Rosen's text. Data stored on a computer disk or transmitted over a data network are usually represented as a string of bytes. Of course, a byte is made up of 8 bits. How many bytes are required to encode 100 bits of data? Well, you're going to round up. So 100 divided by 8 is 12.5. But you're going to round up because you're going to need that 13th bit, or excuse me, 13th byte, even though it might only be half of that byte that has useful data in it. But you're going to need 13 bytes. Another example, example 28, in an asynchronous transfer mode, the communications protocol used on backbone networks, data are organized into cells of 53 bytes. How many ATM cells can be transmitted in 1 minute over a connection that transmits data at the rate of 500 kilobits per second? Okay. Now, in 1 minute, if it's 500 kilobits per second, well, a kilobit is 500,000. And there's 60 seconds in a minute, so 500,000 times 60, or 30 million bits, but each ATM cell is 53 bytes long. So if you multiply, there's 8 bits in a byte, so 53 times 8 is 424 bits. So you could divide the number of bits in the full minute of data transfer by the number of bits in the cells, in each cell, and you divide that, and you use this formula right here. 30 million divided by 424 bits per cell gives you, and then you have to round down. Now, why are we rounding down? It's how many of these cells, complete cells, can be transmitted in 1 minute. So that fraction of a cell is not going to be completely transmitted. So this time we're rounding down. Okay, so that's kind of interesting, the difference in how you answer these questions. Okay, also table 1 in page 150 gives some useful properties of the floor and the ceiling functions. And you can look at these, and in some of the problems, it might call on these properties. Like, for example, this first one, the floor function of x is equal to a number n if x is between n and n plus 1. So that's if and only if x is between n and n plus 1, where it could be equal to n but not equal to n plus 1. So that kind of comes naturally from the definition of what the floor function is. Then you could read the other one for the ceiling function as well. And then these with the negatives, it's interesting that the floor function of negative x is equal to the negative of the ceiling function of x. And if you plug in an actual number, you'll see why that's true. And then this last one, last couple here, it's kind of taking out parts of the sum of two things. And anyway, take a look at those. Okay, so back to the PowerPoint. The last line here, another important function is the factorial function. I'm not sure if you've had familiarity with the factorial function, but it comes up in various programming situations or mathematical situations. F of n equals n factorial is how we read that. N exclamation point. We're not just getting real excited about this, but it's n exclamation point. What that means is multiply n times the number just less than n, so n minus 1, times the number just 2 less than n minus 2, all the way down until you get 1. So you're, like, for example, if it's 5 factorial, we'll go 5 factorial, 4 factorial, 5 factorial will equal 5 times 4 times 3 times 2 times 1. All right, so 20 factorial would be 20 times 19 times 18 times 17 times 16, all the way until we get down to 1. So it'd be a really big number. All right, so that is all the information on functions. There's a lot there. Please let me know if you have any questions. And by all means, do your homework. I know it will take a while, but you know, some of them will come easy, hopefully. Some of them will be a challenge.